Okay, the next piece that we're going to look at, so we kind of know how to test if a number is a zero. Using synthetic division, we can do that pretty easily. The problem is, say we've got some polynomial function, and all we know to do is test numbers using synthetic division. Well, there's a lot of numbers out there, right? You could just begin guessing and pulling numbers at random, trying to find ones that work, but man, there's a bunch of numbers out there, so there's got to be a better way rather than just blindly doing synthetic division to find out if a number is a zero or not. So that's what this rational zeros theorem is. This rational zeros theorem gives us a list of potential rational zeros. Okay, so in other words, a list of possible zeros that we can then use with synthetic division to determine, okay, out of this list of possible zeros, are any of them actually zeros? Okay, and so here's what the rational zeros theorem says. It's a little bit weird, but just hang with me here. First requirement is your polynomial function has to have integer coefficients. In other words, you can't have any fractions for coefficients or decimal values as coefficients. It's got to be integers. Okay, no decimals, no fractions. And the problems we'll be working with will have integer coefficients, so that's not something you really need to worry about, but just know that is a requirement for this rational zeros theorem. So it says, say f is some polynomial written in the following form. Now this is not anything to be scared of. This is just the standard general form of a polynomial where we have different powers of x. Here's x to the n for some value n, maybe x to the fourth, and then x to the n minus 1, that'd be x cubed, and then you'd have several more terms all the way down to your x term and then your constant term. The a's here are just the coefficients. So this might be 3 x to the fourth, where an is 3. Okay, so don't let that throw you off or anything. That's just the standard form of a polynomial. And what the rational zeros theorem says, that's really, this is it right here. If p over q in lowest terms is a rational zero of f, then p must be a factor of a0 and q must be a factor of an. So if we have a potential zero here, or if we have a zero, p over q is some zero, the numerator of that is a factor of a sub 0. That's the constant term. Okay, and then the denominator, q, has to be a factor of an. That's the leading, call that the leading coefficient. Okay, and so how is this helpful? Well, let's look at an example. Let me just jump right into example 3 here. List the potential rational zeros of this function. Now, the two numbers, when we're listing potential zeros, the two numbers we are interested in are these, the first leading coefficient and the constant term. And we want to make fractions using factors of 2 and -6. Okay, where well, let's not write that out, it just gets a little wordy. So we need the factors of 2 and the factors of -6. So first, what are the factors of, let's do -6. What numbers divide evenly into -6? We could have 1 times 6, and then we could also have 2 times 3, right? 1 and 6 and 2 and 3 are all factors of 6, or of -6. We could also have positive or negative on all of these. you know, if positive 1 divides into negative 6, well, negative 1 does also, right? Negative 1 times 6, positive 1 times negative 6. So those are all the factors of negative 6. What are the factors of 2? Well, that's positive and negative 1 and positive and negative 2, right? And so what we need to do then out of these factors is we need to make a list, going back to what this says, of P over Q, where P is a factor of the constant term, Q is a factor of the leading coefficient. So in other words, these are possible numerators, and these are possible denominators. Okay. So potential zeros would be, we could do 1 over 1, we could do positive or negative 1 over 1, we could do 6 over 1, and 2 over 1, and 3 over 1. We could also do all those same ones over 2, right? 2 over 1, I'm sorry, 1, whoops, let me back up here, not 2 over 1. We can do 1 over 2, 6 over 2, 2 over 2, and 3 over 2. So, plus or minus a half, plus or minus 6 over 2, 2 over 2, and 3 over 2. So there's our list. Now, are there any duplicates? Well, if we reduce 6 over 2, that's the same as 3 over 1, right? So this one is a duplicate. Also, 2 over 2 reduces to 1 over 1, so that's a duplicate. We can get rid of those. We end up with 6 potential zeros. Actually 12, because positive or negative, either positive or negative 1, 6, 2, and 3 are all potential zeros, positive and negative 1/2 and positive negative 3/2. Those are all potential zeros. Now that's a lot of zeros. That's a dozen. That's 12 potential zeros. But when you consider that we narrowed that list down from infinity to 6, or I'm sorry, to 12. You know, when we started out looking at that function, we didn't know what numbers might be zeros, so we could just choose blindly random numbers and try them out with synthetic division. But now we've got this broken down to a list of 12 possible potential zeros that we can then use synthetic division with to determine whether those are zeros of that function. Okay, so to go from infinity to 12, it's a pretty good cut. So what's the next thing? So that's the rational zeros theorem. That gives us this list. How is that helpful? Well, let's look at the next problem. It says, find the real zeros of this polynomial function. Now, if you'll look at this, 2x cubed plus 11x squared minus 7x minus 6, that's the same as this previous example where we listed these potential zeros, right? So let me just copy this. And see if I can make it land right here. Okay, so we already know that these are potential zeros for that polynomial. The only thing to do then is to try these out. So let me say, all right, I wonder if positive 1 is a 0. Okay, well, if 1 is a 0, we can set this up with this synthetic division. 2x cubed, 11x squared, minus 7x minus 6. And we should be able to run this through our synthetic division. If 1 is a 0, then we should get a remainder of 0, right? So 1 times 2 is 2, that's 13. 1 times 13 is 13. If we add that, we get 6. And wouldn't you know it, 6 and negative 6 is 0. So that tells me that positive 1 is a 0 of this function. That also tells me, okay, if 1 is a 0, then x minus 1 is a factor, and it's x minus 1 times, remember what we did earlier, that's 2x squared, because we started with x cubed. After one round of division, we're at x squared, plus 13x plus 6. Okay. So we found 1, 0. Now what's cool about this process is once we find 1, 0, it's easier to find another 0. Okay. This piece right here, this smaller polynomial, we call this a depressed polynomial. Okay. Once we kind of chip away at it and factor it a little bit, it becomes a depressed polynomial, as I'm sure, this is my joke for this part of the section, as I'm sure many of you are now depressed because you're sitting in the middle of a math lecture. It's also depressed, so you're good company here. That's a depressed polynomial. Now what's good about this, what's helpful about that depressed polynomial is that's a third degree polynomial, right, that we started with. So there's at most, we got a maximum of 3 zeros. We found 1, that means there could be 2 left, and wouldn't you know it that those 2, my other 2 polynomials, reside inside this depressed polynomial. My other 2 zeros are the zeros of this smaller polynomial, okay? So what that's helpful for is as I continue this synthetic division process, what I can do is I can actually save myself some work and use this depressed polynomial. I'm drawing another division bar, and I'm going to test my zeros in this function right here. 2x squared 13x 6. That's 2, 13, 6. Okay, so you just need to go back to your list and say, all right, what's another potential 0 here? I don't know, maybe 6. Positive 6 is a 0. Let me just try that. I'm just stabbing in the dark here, but that's on my list. So 2 and 6 would be 12. Add those, we get 25. This does not look promising. 6 and 25 is 150, and that's 156. Okay, well that didn't really work out. Pencil is good here because now I can just erase. Now why didn't that work out? I didn't get a 0 remainder, right? So let me try negative 6. Bring down the 2. That's a negative 12. If we add that, we get 1. Negative 6 and 1 is negative 6. And there's my 0. Cool. So I found another 0. That means my function is now, I've already got x minus 1. I found negative 6 is a 0. That means x plus 6 is a factor, and that last piece is 2x plus 1, right? That comes from this right here. Since this was x cubed, this was an x squared, that means that's an x, okay? So 2x plus 1. Now the question is, what's my last 0, okay? Well, if I have 1 0 left, it's in this last piece right here. 2x plus 1, if that's 0, then 2x, if I subtract 1, I get 2x equals negative 1, and x is negative 1/2. So that's my last 0. So if I want to list those, they are positive 1, negative 6, and negative 1/2. And my function, factored completely, is x minus 1, x plus 6, and this last piece, instead of 2x plus 1, I'm going to put x plus a half. Really, I'm factoring a 2 out of this, and that 2 is going to land all the way up there at the front. Okay, so you'll see this is kind of the standard way of factoring these polynomials, where in this case, since I had a 2x, I factor that 2 out. It comes to the very front here, and now I can look at this and see, okay, x minus 1 plus 6 and plus a half gives me my zeros of 1, negative 6, and negative 1/2. Okay, so there I'm done. Really, for this problem, all I had to do was find the zeros, find the real zeros. That's this part right here. But the factoring that goes along with that is very helpful as well, and you'll see that in the homework. Okay, so that's worked, that's finished. Now there's one part that I've left out. There's one other piece of this that is incredibly important and incredibly useful that I've kind of glossed over up till now, and some of you may have thought of this already. If you'll recall, when we introduced polynomial functions, we said that the zeros are the same as the x-intercepts, right? So you could actually save yourself a lot of trial and error, a lot of guesswork, because we do have graphing calculators. If I graph this, 2x cubed plus 11x, whoops, okay, 2x cubed plus 11x minus 7x minus 6. So if I graph that, whoops, I left out a square, didn't I? Let me back up and try again. That should look better. What do you see? What do you see? Well, x-intercepts, right? Where is this thing crossing the x-axis? Well, we learned in the last section we can calculate the zeros. So maybe I want to look at this one that's in the middle here. So let's go to the left above that 0, and then let's arrow to the right below that 0, and we get negative 0.5. Well, lo and behold, isn't that one of the zeros we came up with on our list? It's negative 1/2. And it's, it doesn't take a stretch of the imagination to say, okay, that looks to be crossing at 1. Well, yeah, sure enough, if x is 1, that's a 0. And if I can count back 1, 2, 3, 4, 5 to negative 6, that's another 0. So our graph is very useful. We can actually get a really good picture of what our zeros are from our graph. Okay, but you don't want to use the graph all by itself. You'll see in the next section when we start talking about complex zeros that this synthetic division process and kind of chipping away at it 1 0 at a time is very useful, very useful. But this is a tool at your disposal, and definitely feel free to use the graph to help out as you're looking for these zeros. So here's the whole process, what we just went through. That is in the notes that are posted on Blackboard, so you can download those and review those steps. We're going to go on to example 5. Find the zeros of this function and write it in factored form. So basically the same thing we just did. X to the 5th means there's no more than 5 zeros. So we could have up to 5 zeros in this function. Really quickly, using the rational zeros theorem, again we're looking at the leading coefficient, which is a 1, and then that 16 there. So what are the factors of 16? 1 times 16, 2 times 8, and 4 times 4, right? So we get those factors. The factors of 1, well, that's kind of trivial, plus or minus 1. So potential zeros, again, the factors of the constant term, these are my numerators. Okay, so 1, 16, 2, 8, and 4 all over 1 just gives us that same list back, right? We put those over 1. Okay, so these are potential zeros for my function. The next thing I would recommend doing is graphing this thing. Rather than just starting to hack away at that list of 10 potential zeros, save yourself some work and just look at the graph. We've got x to the 5th, and I'm going to have to switch back and forth here to remember all this, minus 5x to the 4th, plus 12x cubed, make sure you copy all this right, minus 24x squared, plus 32x minus 16. A lot to type in. If we hit graph, what do we get? Okay, we get some stuff happening right in this little area right here. So it might be helpful to zoom in on that just to see what it looks like. I'm going to say that's at 1, and then another touch, an x-intercept touching at 2. Now, you got to remember some other things going back to section 5.1 that may be helpful here. What do we know about an x-intercept that crosses the x-axis and an x-intercept that touches the x-axis? When did we talk about when a zero crosses or touches? We talked about the multiplicity, right? A zero that crosses the x-axis has odd multiplicity. A zero that touches the x-axis has even multiplicity. Okay, so we would say that the 0 at 1 has odd multiplicity. At 2, it has even multiplicity. Now that's very important for what we're going to do on this next piece here. So to show why that's important, let's do our synthetic division with 2. Starting with x to the 5th here, that's a 1x to the 5th minus 5x to the 4th plus 12x cubed minus 24x squared plus 32x minus 16. Okay, we're going to bring down the 1. 2 times 1 is 2. We add that, we get negative 3. Multiply, we get negative 6 plus 12 is 6. Multiply again, we get 12 plus negative 24 is negative 12. Multiply again is negative 24. If we add that, we get 8. 2 times 8 is 16, and remainder of 0, just like we expected. Now, even multiplicity. We just said this 0 is even multiplicity. What that means is it's a repeated 0. And what that means for you as you're doing the synthetic division, if you know a 0 is repeated, like this positive 2, since it touches the x-axis, go ahead and repeat that synthetic division again with the same 0. So bring down the 1, multiply and get 2, plus negative 3 is negative 1, multiply is negative 2, add and we get 4, 2 times 4 is 8, we add that, we get negative 4, 2 and negative 4 is negative 8, lo and behold, another remainder of 0. Again, that's a repeated 0, has even multiplicity. And really and honestly, it could have multiplicity all the way up to 4, because this is a 5th degree polynomial. Could be that this 0 at 2 is a multiplicity 4, the 0 at 1 is a multiplicity 1. So you really need to keep going here. Try it one more time, because it could be 4th, or a multiplicity 4. Maybe a little unlikely, but we're going to try it anyways. And we get a remainder of 8. Okay, so that tells us we've pretty much run out on that one right there. We've gone as far as we can go with that 0. But we know that 1 is a 0, so let's continue this process with 1. 1 times 1 is 1. Add that, we get 0. 1 times 0 is 0. That's a 4. 1 and 4 is 4. And that's a 0. Okay, so I know that 2 is a multiplicity 2, 0. 1, I know it's odd multiplicity. Again, this is a 5th degree polynomial, so maybe it's the case that 1 is a degree, or a multiplicity of 3. It's repeated 3 times. That would still be odd. That would still fit inside the 5th degree polynomial that we've got. So I need to try it again, just to make sure it's not repeated anymore. And I get a remainder of 5. So at that point, I've exhausted that 1. And really, going back to my graph, that's as far as I can go. There were not any more x-intercepts on that graph, which means there are no more zeros. Okay, once I've kind of run out on that synthetic division and gone as far as I can go with 2 and with 1, the 2 zeros I know I've got, well then that's as far as I can go. So what are we left with? That's the question. What is our function? Well, I know I had 2 for a 0, so that's an x minus 2, and it was multiplicity 2, so I'm going to square it. I know I've got a 1 for a 0, so that's an x minus 1. Whoops. And then what am I left with? Okay, let's back up and think here. I started with an x to the 5th polynomial. After one round, I was x to the 4th, then x cubed. So this is x squared, right? So this is an x squared, 0x, so no x term, plus 4. So there's my factored function, and I said my zeros were 1 and 2. Now, could there be any more zeros left in this piece right here? X squared plus 4. Let's explore that real quick. If that thing is 0, can I solve that? Well, that would mean x squared is negative 4. And if I take a square root, I get negative 4 under a square root, which is no real solution. Can't do a square root of a negative and get a real number solution. Okay, so I'm done. I'm just talking about real zeros here, so I can't go any further. So we're going to get into the next section and talk about, well, what if we allow square roots of negatives? In this case, then we can continue. If you remember, a square root of negative 4 is a 2i, if we use imaginary numbers. And with that in mind, we could continue factoring that and continue working it down. But that's it for this section. Oh, I'm sorry, that's not it for this section. I'm sorry, there's one more thing we have to do. Solve polynomial equation. Okay, so, and this will go quick here. So say we had an equation to solve like this. Had a big polynomial equation, all that equals 0. Really, we can solve that pretty easily using what we just learned. First thing we do is set it equal to 0, which we have done. It's equal to 0. The next step is to factor that. Now, if you'll look real closely at this left side of that polynomial, That's the polynomial we just used in that previous problem, right? So we know that this is x minus 1 times x minus 2 squared times x squared plus 4. We just factored that in the last problem. So we factor it, and then we use the zero product property to find solutions. Now the zero product property, you've used that before. All that says is we've got 3 factors here multiplied that equal 0. So one of them had to be a 0. So there's kind of 3 cases here because there's 3 factors. If this one is a 0, then x equals 1 is a solution. If x minus 2 is your 0, then positive 2 is a solution. Well, x plus 4 is 0. We just said that has no real solution, right? We did that just a second ago. So what are the solutions to this thing? Same as the zeros we just found, okay? So that's kind of the way that works. Once you've factored that, found the zeros, that's the same as solving that equation when it's equal to 0. And that is the end of this section. So make use of that graphing calculator. It's a big help for finding where those zeros are, but also don't overlook the synthetic division. It's very helpful when it comes time to factor. So if you have any questions, let me know.